So in section 2.1, we did a great job of taking a arbitrarily sized matrix, turning it into a triangular system, checking to see what the rank is, if it's full rank, using back substitution to get a nice solution vector, and even came up with a metric to see how good of an answer we got using residuals. What left is there? It seems like we've solved the problem. We ought to move on to chapter 3. Well, we're not quite done yet because we have a serious issue in front of us that is sneaking up and ready to bite. And that is that the system that we came up with is vulnerable. It is vulnerable to the data. Ooh, that sounds awful. I'm really saying that if you throw the wrong data at that algorithm, the algorithm might either completely fail or it might give you fallacious results. That's depressing. How am I going to fix that? Is everything we just learned useless? Well, no, it isn't useless, but it's going to need a little bit of extra help. So now the methods in 2.1 will be renamed, and we're going to call them the naive Gaussian reduction methods, and we're going to try to be a little less naive as we move into subsequent sections. What goes wrong? Well, the main thing that goes wrong is the main diagonal. We're going to take a look at what happens if somebody throws in a 0 into any value at all on this main diagonal. What happens to our algorithm? Well, let's just take a look back at this little 2x2 example. Well, this is the algorithm that we agreed on at the end of section 2.1. It's the triangularization algorithm. We still have to do back substitution. But we have to do this first, and if we apply this very simple matrix to this algorithm, we're going to end up dividing somewhere by a diagonal. We're going to go through every diagonal element and divide by it somewhere. And right out of the chute, we have A11 that's equal to 0. Well, dividing by 0 is not a pretty picture. We end up getting what we call machine overflow, and you'll get an error message, and you won't even, I mean, your goose is cooked. You're really hosed at this point. You're in trouble. There is nothing you can do. The computer crashes. It pulls a hand out and slaps you a few times, and you're not very happy. Okay, and this is on a very simple system. So let's take a look at back substitution. What happens there? Well, it looks like we divide by the diagonals there too. Now in this case, it's not really quite so serious because, to be honest about it, backward substitution is only used after you triangularize the data. And if you ended up getting a 0 in the diagonal after you triangularized it, that meant you had a singular system. So we won't worry about this so much, but the triangularization itself is really a big issue that we're going to need to look at. Well, so what do you do? In fact, maybe you should ask, is there even a solution to this system? Maybe that's the problem. Maybe the algorithm's okay, but there isn't any solution. Well, we know how to check that. Here is our matrix A, and we could write it as A, B, C, D, or we could write it as the numbers that we've been given. And the way we determine if a solution exists is to check the determinant. If the determinant is 0, no, then it's a singular system and you're not going to get a unique solution. Well, let's do the determinant. If we take the determinant, we take the product of the diagonal elements minus the product of the off diagonal or the minor diagonal, and we end up getting a -1. Well, that's okay. As long as you don't get a 0, a solution exists. So we have an inverse, we have a solution, it is not singular, and yet our algorithm is going to fail. If we keep working on this thing, we can take the inverse times the b vector, and we come up with a solution. So by hand, we know the solution, the true solution is 1, 1. And yet our algorithm is going to blow up. Okay, not pretty. There's another situation that's actually worse than the one that I just described. If I take that same matrix and instead of putting a 0 in the upper left-hand corner, I just put a really small number, what happens then? Well, let's check the determinant to see if a solution exists. we'll take epsilon times 1 minus 1 times 1, and that will be epsilon minus 1. And that is never 0 unless you unluckily choose epsilon equal to 1 itself, which wasn't the point. We were going to pick a really small value of epsilon. But even if you did pick epsilon equals 1, it's very obviously not going to work because you have two identical rows. So we don't have a sufficient amount of equations. So let's suppose epsilon is just small. It's not 0, but it's small. What's going to happen? Well, we have our inverse that we could calculate directly using our formula, and we could plug in the outcome vector, and we could create ourselves an exact solution vector. That would give us x1 equals minus 1 over epsilon minus 1, and here we have x2. If you ask what happens if epsilon's getting really tiny and very close to 0, you can see that epsilon becomes negligible and x1 is approximately equal to 1. And again, if epsilon is very, very small, x2 is approximately equal to 1. Well, that's good because that is what we expected. That's what we got before when we used 0 directly. So theoretically, this matrix has no problems at all. This thing should work just fine on some algorithm. Now let's say that our epsilon is pretty small and it's starting running out to the edge of our significant digits. If you're comparing this to a big number like 1 or 2, then we're going to have numbers that if we try to add or subtract are going to end up, one or the other is going to look like noise. Well, let's look at that more specifically so you can see what I mean. If I want to solve this thing by hand, but I want to use floating point arithmetic in the process, then I would just apply the normal row reduction that I would usually do. So this particular expression will accomplish in putting a 0 in the lower left-hand corner, and I'm starting to introduce this f sub l term, meaning that my arithmetic is all going to be done in floating point arithmetic, so I have to be careful about that. And I should ask, since the very first row reduction produces this step, what does 1 minus 1 over epsilon look like, and what does 2 minus 1 over epsilon look like? Well, if epsilon is really, really tiny, like less than 10 to the minus 7th, and it's in single precision real, then 1 over epsilon is going to be a really big number, like 10 to the 7th or bigger. Trying to do any addition or subtraction between the number 1 and a number of the size of 10 to the 7th is going to just come back with the 10 to the 7th. This 1 is going to be in the noise level, and it's going to fall off the right of the mantissa when you try to do the subtraction. Same thing's going to happen here when you take 2 minus 1 over epsilon. The 1 over epsilon is going to dominate because epsilon is really little, which means its reciprocal is really big. So that means in floating point notation, we could just as soon take the 1 minus off, or take the 1 off and take the 2 off, and just leave what's left over. And that's what you would actually be seeing on the computer if you did this in floating point notation. Well, let's continue to solve this thing. We'll do our back substitution, and we won't go through all the details. But when we're all said and done, we end up getting x1 is equal to some number times 1 minus x2. Well, x2 came out like you expected. x2 is equal to 1. We got that when we did it by hand. But if I plug a 1 in here, I'm going to get a 0, and I'm going to get 0 times a big number, which will produce 0, and my solution becomes 0, 1, rather than what we know it should be, which is 1, 1. That's a long shot off. I mean, that is a radically bad answer. And that's just not tenable. We can't have that. What's even worse is the computer would have done it. It would not have given you any errors in the process. It would have dutifully done these calculations and given you garbage, and you might not have known that anything was wrong at all. So this is really a more serious problem than when the computer program just blows up. Okay, so I've painted a big problem. Actually, I painted 2 of them, and I haven't given you a solution, which is really a nasty thing to do, but that does give you motivation to come back to section 2.2b, where we will come up with a method that will avoid this predicament.